In the past, we've dealt with elastic potential energy, but I always had to give it to you. We didn't have to calculate it. In this video, we're going to talk about how to deal mathematically with springs. So the first thing we're going to talk about is what's called Hooke's Law. And Hooke's Law is the relationship between the force on a spring and how far it changes length. We say the change in length of the spring is directly proportional to the force applied. Okay, directly proportional means as the force gets bigger, the distance the spring gets stretched out is going to be bigger, and that makes sense. Directly proportional means that it's going to make a straight line. We call x the distance stretched. Have force, we get a straight line like this. Mathematically, we can figure it as F equals kx. Now, x actually is the actual length of the spring. It is the change in length of the spring from its equilibrium position. K is going to be something called the spring constant. Okay. Now, it's not a constant like big G, the gravitational constant is. Big G is 6.67 times 10 to the minus 11 everywhere in the universe. That is a real constant. The spring constant is only constant for any given spring. So if I have a single spring, I know that the spring constant will be the same, but if we switch to a different spring, it can be different. But it's a measure of strength of a spring. So the stronger the spring is, the harder it is to pull out, the bigger the value you are going to have in K. Now, Hooke's law is kind of like not a law that applies to everything either. If I had a spring or something that did, say, something like this does not obey Hooke's. So here's an example. The spring is 0.4 meters long. It stretches to 0.6 meters when a 10 kilogram mass hangs from it. What is the spring constant? So we might do this as a lab. All right, we would hang a spring. The equilibrium length is 0.4 meters because there's no mass on it. But then we're going to hang a mass on it and stretch out. And the mass is 10 kilograms. And now its new length is 6 meters. That's going to give me x. Remember, x is the change in length of the spring. It's 30.2 meters. The force on this, there's a 10 kilogram mass hanging from it. So we have to use mg to find the force of gravity on that, and that's what's pulling down on the spring. So that's about 100 newtons. So then we plug in kx. We would get 100 newtons. K, meters. Value for K is 500. We need a unit for it. It doesn't have its own, but we got it by dividing 100 newtons by 0.2 meters. So it's 500 newtons per meter for the spring constant of one spring. Where this really gets important is when we're dealing with energy in springs. And the equation for that is PES, the energy stored in the spring, is 1/2 K squared. So here's an example of where we might use that. Spring with a spring constant of 80 newtons per meter is compressed to 2 meters. It is then used to fire a 1 kilogram mass across the friction of the surface and up the slope. It comes to rest at point C, so we can move that P0 over here. We also have a spring constant, K is 80 per meter there. And now we can solve this problem. Let's go look at point A. Okay, at point A, all of the energy is stored in the spring. There's no kinetic energy because it's not moving yet. There's no potential energy because there's no height. So our P is 0. Height is 0. K is 0. Because the velocity is 0. All of the energy is stored in the spring. So now I can use this new equation to find it. The distance to equilibrium is 2 meters over here. And then that's going to give me 160 joules of potential energy stored in the spring. And then the total energy is 60 joules. Now I can move on to point B. Now the spring is no longer compressed, so my PES is going to equal 0. I still have no height, so PE equals 0. Okay, I want to find my KE. But I know the total, since there's no friction, there's no energy loss, there's going to be 160 joules. So therefore, the kinetic energy has to be 160 joules. And from that, I can find the velocity. KE is 1/2 squared. 60 is 1/2. Mass is 1 kilogram. P squared. And I'm going to get B equals 17.9 meters per second. Alright, now if I look at point C, by the time we get to point C, the kinetic energy is 0. The spring is no longer compressed, so that's going to be 0. And figure out our potential energy, but again, we know the total is 160. That means the PES has to be 160. So then I can find the height there. So 160 equals the mass of 1 equals 10 times h. H is